Okay guys, so we have CodeChef starters 140 Div2 and let's get started with the problems. So first of all we have problem A here. So we are given an array A of size n and we want to make a permutation using this array. So we have to find whether there exists an array B consisting of n non-negative integers such that array C constructed as Ci equals to Ai plus Bi is a permutation, right? You can read a definition of a permutation here if you do not know that. Uh, Pause the video and read it first. So yeah, the constraints are not much of an issue here. Let's just jump to the solution here. So let's take the first test case here. We have we have to answer yes or no whether this can be converted to permutation or not, right? So we start with the first example here. We have 41321, 41321, right? And we want to convert this into 1, 2, 3, 4, 5, right? So we can add elements. We can add elements. We cannot subtract, right? We can add elements, but we cannot subtract the elements. That is the requirement of the question. So, do you think it is appropriate to sort the array first? Think about this uh, carefully. Do you think it is appropriate to sort the array A first and then try to convert it into C? Well, yes, we should sort the array A first because uh, because obviously the shorter elements will be converted to the shorter elements and the larger elements will be converted to the larger elements because we have to add, we cannot subtract, right? So that's pretty much obvious. We just sort this array and try to convert this into C. So how do we convert this into C? We can see that it's possible to convert this array into C because we can add non-zero integers to all the elements and convert this into C. For example, we'll add the array 0, 1, 1, 1, 1 to this array, or rather to this array, and convert this into C. It's possible. Let's just take another example. So we have I think it was the last example. We have 1, 1, 1, 1, 1, no, 6 and 6, right? And we want to convert this into 1, 2, 3, 4, 5, and 6, right? So we can convert this into this by adding 0, convert this into this by adding 1. We can add 1 here, we can add 2 here, we can add 3 here. We cannot add anything here. Since we cannot add anything here, it's very obvious to notice that we cannot add anything to the elements ahead of this element also, because all this will be greater than or equals to this element, right? So since we cannot add anything to this number, we cannot add anything to the numbers further and so on. So basically 5 cannot be achieved. 5 cannot be achieved using numbers from here, and all the numbers on the left hand side are already used. So basically it's not possible. The answer will be no. So the answer will be no whenever we have such a condition that C of I is less than A of I, right? Then it's just not possible. Uh, that's the only condition, I think. We do not need to check for any other thing, and our problem will be solved. So this does not need much of an explanation. Let's just jump to the solution here. Uh, okay, this is the code here. You take the input of all the numbers, and then we sort the array A, right? And then we iterate from 0 to n, and if we just check the condition that if ai is greater than I plus 1. So since we are iterating from 0 to n minus 1 here, so the permutation ci will be equals to I plus 1, right? That's why I've compared it to I plus 1 instead of making an array C separately. It's just the index. So if ai is greater than I plus 1, then it's not possible, right? So we just print no, and then we return. Otherwise we print yes to the solution, right? That's the answer here. Yeah. effect in I plus 1, then no. The second condition is pretty much redundant. I must have written it in the flow of the contest. It basically is if AI is less than 1, then it is not possible. But AI will be never less than 1 because you can see the constraints here. Uh, AI is from 1 to n, so it will never be less than 1, right? So the second constant is redundant. We can just use the first constant and find the answer. So that's for question 1. Let's jump to the next problem.
This is second problem from CodeChef Div2. You can pause and read the problem. So in the question we are given n and m and two arrays a and b, both are of length n, and here m denotes the number of children, as you must have read in the question. So suppose a is a1, a2 till n, and b is b1, b2 till bn. So in the problem, what we have to do is we will select one element from the array A. Let's say we selected AI, and another element from the array B. Let's say we choose BJ. Then we have to mix them, and after mixing we have to distribute the total number of elements present in AI plus BJ equally among m children, which uh, that is AI plus BJ should we should divide a total number of elements, that is AI plus BJ, equally among m children. This implies AI plus BJ mod m must be 0 for this process to happen. So this implies AI AI mod m plus BJ mod m should be 0. So uh, this there are two cases. If AI mod m plus BJ mod m equals to 0, the first one is either AI mod m is equal to 0 and BJ mod m is equal to 0, or the second one, AI mod m is equal to m minus BJ mod m. So where how this came, suppose you shift this BJM to the left hand side, so there will be AI plus BJ mod m equals to m, and if you take modulo again, then it will be AI mod m plus BJ mod m equal to 0. That is same as this one. So we will be using these two properties to solve our problem. So we had AI mod m equals to 0 and BJ mod m equals to 0, or AI mod m is equal to m minus BJ mod m. So in this problem, we have to find the total number of ways in which we can choose one element from the array A and the second element from array B and divide them equally among the m children. So for doing this, uh, suppose for doing this we will use map, because this is a typical problem which can be solved by using map. So in map we will store the frequency of AI mod m and BJ mod m. Suppose one map is MP. In this we will store the frequency of AI mod m, and second one say MPE. In this we will store the frequency of BJ mod m. So suppose uh, and then we will traverse any one of the maps. Let's say we traversed the map MP, and suppose AI mod m value is, let's say, x. Then uh, corresponding to it, suppose AI mod m value is x and its count is, let's say, count x. So corresponding to this, there will be only we need to find uh, from the map MPE which elements have its modulo equal to m minus x from this property. Suppose uh, this is its count is equal to count y. Let's say this is y equals to m minus x. I'm using this property. So so the total number of ways, then this will be equal to count x into count y. So similarly we will do this for uh, uh, all values that is present in the map, and then we would sum it up. And but there will be a case left when AI mod m equals to 0 and BJ mod m is equal to 0. So this can be also this is also simple. Suppose we have total count of AI total count of MP0. This will correspond to AI mod m equals to 0 into MPE 0. So if we multiply these two, this will take care of this case, because in this case also we can divide equally among m children. So it's simple. You can see its code, then it will be more clear. So this is my code. So there are two variables n and m. I have taken the input in the arrays arr and prr. I have created two maps, MP and MP, as I have explained earlier. Now here I have stored the frequency of ARR at I modulo m, and here I have stored the frequency of PRR at I modulo m. Suppose you can see an example. Suppose we have m as 5, and suppose our array A is 1, 2, 3, 4, 5. Suppose B is also 1, 2, 3, 4, 5. So taking modulo, then 5 would only this will convert to 0, and here this will convert to 0. So corresponding to 2, the value of m minus 2, that is 5 minus 2, this will be equal to 3. So if you combine these two, that is 2 plus 3, then its modulo would be divisible by 5. This is just an example to show that what we are doing is correct, by storing the frequency of A at I modulo m and B at I modulo m. So initially our answer will be 0. Now I will traverse one of the maps. Let's say I'm traversing the map MP. You can traverse the map MP also, no difference. So we will increase our element. So suppose uh, we have the first element as x dot first. Suppose x we have its first element x dot first. So what we need, its pair would be m minus x dot first. For x dot first, its pair would be m minus x dot first, and MPE of x minus x dot first will give its total uh, total count for all the elements which have uh, modulo m minus x dot first. So if we multiply these two counts, we will get a valid answer, and we will sum all the answers. And this is the second case when our modulo are 0. So we will simply sum the total count of MP0 and MP0, and then we will print it. Hello friends, this is the third problem from CodeChef Div2. You can pause and read the problem. So in this problem, you are given a permutation P of length n. Suppose n is 6, then P can be 3, 2, 1, 4, 5, 6. It can be any permutation. So we have defined goodness as k. So what is it? Suppose you divide our permutation P into various subarrays. Suppose you split it in this way. Then its goodness is defined as uh, the maximum number of subarrays such that the sum of each subarray is same. Which means suppose uh, these are the subarrays. This is of length 2 and this one 3, 2. Another subarray is 145 and the other is 6. So their sum should be same. In this case, it's not same. So it's not this k equals to 3 is not valid. So here k is since we have split it in 3 subarrays, the value of k is 3, but this is not a valid uh, valid k as it is not good. So for solving this problem, we will use the concept of AP, arithmetic progression. So we can think in this way. Suppose what could be the maximum value? What could be the maximum number of subarrays? It can be n. This is the maximum possible, where each subarray is of length 1. That is, uh, first subarray is 3, second is 2, and so on till 6. So, but we can clearly see that this case is never possible. That is, the value of k can never be n, because it is permutation. So no two numbers are same. So we can uh, move to other way. That is, uh, the length are each subarray is of length 2. That is 3, 2, 1, 4, 5, 6. This is also a valid one, but uh, as you can see, this is also not valid. So solving this one, we will use the concept of arithmetic progression. That is, you very well know, suppose these numbers we know are in AP, so we can make an observation that the sum of first and last number are same. See, 1 plus 6 is 7, 5 plus 2 is 7, 3 plus 4 is also 7. So this is a concept from arithmetic progression, and we will use the same concept for solving our problem. So now, so in this case, suppose here uh, n is 6, so the maximum value for k is 3, as there are 3 subarrays, 1 2, I mean there's 1 and 6 can be clubbed together. Suppose our permutation is this 1 6 3 4 and 2 5. So this is a valid permutation, and here this is maximum also because k is equal to 3. This is the max possible. So there are two cases. First one, when n is even. Second, when n is odd. So for the case for n is equal to even is pretty simple. We can simply club the first and last elements and print them. So in this problem we have to keep the permutation t, which has maximum goodness. So for n equals to 6, this is a valid permutation which will give the uh, max value of k. So for n equals to even, when n is even, this is pretty simple. Just club the first and last elements. Starting from here, we will first club 1 and 6, then 2 and 5, then 3 and 4. The case when n is odd. So suppose n is 5. 1 2 3 4 5. So we know n minus 1 will be even. Then if n minus 1 is even, then this becomes the case 1. So for the uh, so for 1 to n minus 1 elements, this will become the case 1. So we could simply combine the first and last elements in this subarray part. We can combine 1 and 4, then we can combine 2 and 3. And for the last element, we can leave as it is, because after clubbing the values are 1 plus 4, which is equal to 2 plus 3, which is equal to 5. So we could leave 5 alone, and we could club in the left n minus 1 part, as we have done for even case. So it's pretty simple. uh, its implementation is quite simple. I will show you in my code. So here is my code for this problem. This is n. Now so suppose we are given n as 6, so this will point to the first, a will point to first element, b will point to the last element. So now the number of times we need to club is n by 2, because there would be since n is 6, we need to club it n by 2 times. So I have, so this is the case when the number is even. So I have run a loop from uh, 0 to n by 2, and after clubbing I have printed them. So first we will club 1 and 6. So 1 and 6 will be printed. Then the next elements to club would be, we will increase this by 1 and we will decrease the last element by 1. So increased a by 1, decrease the last element by 1, and then we will print them again. So this will form sequence like this. So this is a varied permutation because these are same, and the value of k is also maximum. And this is the second case. So as we have discussed, as n by 5, uh, I will club the n minus 1 part. So for the n minus 1 part, I will decrease the last element. So this will be 1, 2, 3, 4, and the same process will be repeated. But uh, after running loop from 0 to n by 2, we will print the last element also. Uh, and this is the answer. So it will, suppose for this case, first it will print 1 and 4, then it will print 2 and 3, and after that it will print 5. So these are the subarrays 1, 4, 2, 3, and 5, and this is a wide subarray with max k value. Reference, this is the fourth problem from CodeChef Div2. You can pause and read it. So in this problem, we are given a tree. It has n vertices and n minus 1 edges. This is property of tree to have n vertices and n minus 1 edges, and it also does not have any cycle in it. So you're additionally also given an array A, which store the value of each vertex. So each vertex has certain weight, you can say. Suppose this is a1, a2 till an. These are the weights assigned to each of the nodes. So in this problem, uh, so we are given a tree. Suppose this is a tree. Let's say it is 1, 2, 3, 4, 5, 6. So each node has a value, that is, let's call them AI. So each one of them has a certain value attached to it. So in this problem, for we can remove all the nodes which has odd degree. So as you can see, this node 2 has odd degree, that is this 1, 2, 3, as there are 3 edges incident to it. Similarly, uh, the node 1 is also odd currently because there is only one edge which is incident to it. So we need, in this problem, we can remove all the odd degree nodes, and there is a score. Initially the score is 0. So after you remove one node which has odd degree, you can add its score. You can add its value to score. Its value would be AI. You can add it to the score. So in this case, in this problem, you have to maximize the score, and you have to print how you will maximize it. I mean, how you will remove the nodes in such a way that the score is maximized. So for this problem, if I ask you what is the maximum score that you can form, so its simple answer would be these sum of values of all the nodes, that is a1 plus a2 plus an. This could be the maximum score. Max score. It can be the all the sum of the values of all nodes. This is the maximum possible, but it will only be possible if all the uh, nodes are of odd degree. So there are few observations that you can make. Suppose this is so one observation you can make is that all the leaf nodes are of odd degree. You can see node 7 it has odd degree, node 2 it has odd degree, 1 it has odd degree, 4 it is odd degree, 5 it has odd degree. So you can remove all the nodes. You can remove nodes, and this can be a valid way. But if you remove a node, then the under node through which it was connected, it will change its degree. Suppose if it was odd, then it will convert even, or it was even, then it will convert to odd. For example, if you remove, then the degree of 3 will change from odd to even. So let's do an experiment. Let's see what happens if we start removing all the leaf nodes. So suppose we first remove 7, then we remove 2, then we remove 1, then we remove 3, then we remove 5. Now there is node 3 and 6 left. Now both of them has odd degree, so we can remove any one of them. So at the end only one node is left, but now it has even degree. Even degree in the sense it is connected to, it has zero number of incident edges, so its degree is even. So we cannot add its value to our score. So this is a second observation, that uh, there will always exist a process consisting of removing all the leaf nodes, such that at the end only one node is left, which will be of even degree. You can take any graph. Suppose you take this. So at the end only one uh, so there will exist a process of removing nodes, such that at the end only one node is left with even degree, and all the other nodes which we previously deleted, they were of uh, odd degrees, and that move would be removing all the uh, leaf nodes. Suppose we'll remove this node, then our graph would be this. Now these two are the leaf nodes, so we can remove anyone. Suppose we remove this, then our graph would be this, and then again we remove this, then only one will be left. And but we cannot add this to our scope uh, because it has even degree, but all the other nodes that we previously deleted, we can add them to our scope. So for getting the max value, uh, what we can do is at the end only one node is left. So to maximize the score, we will like to have the last node that we remove that has minimum value. Suppose this node has this node is n. Suppose this is node n. So its value is minimum. That is an is minimum. So we like that the only node that is left at the end, it has the minimum value. And I will show you there always exists a way such that uh, we can have only one element left to it, only one node left at the end, and we can always decide them. So consider this example. Let's suppose that this node was the minimum. This node has minimum value. So we will like that this node is removed at the end. So what can we do? Uh, we will we can move to its from here. We will start moving to its leaf nodes, and we will delete them. Suppose let's name them 5. So from 1 we will move to 2. From 2 we will move to 5. So here 5. This is a leaf node. So we will remove it. Then from 2 we will move to 4. This is also leaf node. So we will remove it. Then from now after removing 5 and 4, our graph would like this. Now earlier this has a degree as 3, but now it has degree as 1, so it has become leaf node now. So we can simply remove this, and then after that this node 3 is also leaf node, so we will remove this also. So finally the one which is minimum is left. So for solving this problem, it is clear example of using DFS. You can see what we did. We moved to its neighboring nodes, and then we went in depth till we reached the leaf node, and from the leaf node we started deleting the element. So it is clear example that we have to use DFS for this problem. So first we will identify the minimum value and its index, or simply we are just concerned with the index which has the minimum value, or the node which has minimum value. So for solving this problem, we will run a DFS. We will start our DFS from that minimum index. Suppose this was the node 1. We'll start DFS. So while traversing in the DFS, uh, when there will be back propagation. What do I mean by back propagation? That after after calling DFS, when there will be back propagation, suppose let's see an example. Suppose suppose this was our menu. So we will start our DFS call from this node 1, then it will call for node 2, then node 2 will call for node 5 and node 3, then node 3 will call for node 4, then node 5 will call for node 6. Now, when all the nodes will be called, all of them has we have the visited array, all of the nodes would be visited. Now, after that, there will be back propagation. That once it has reached, say, a leaf node, then it can no more make a DFS call. So the function will return. This is mean by back propagation. So when the function will return, uh, I will simply print the elements. For example, first node 6 will be removed in the back propagation. Then in the back propagation, 5 will be removed. Uh, Similarly, the further DFS call for 4 and 3 would also be happening. So the 4 will remove first, then 3 will remove. Now for 2, we have visited all its neighboring nodes. So this will converge to this, and then in the back propagation step, 2 will come. So we will remove 2, and at the end, 1 will come. So, but we cannot remove the minimum element, so we'll print only. So this will be our answer. This is a value answer. You can see first we can remove 6, then we can remove 5, then we can remove 4, then we can remove 3, then we can remove 2. All of them will eventually become a leaf node, and but and then only the node which is minimum is left. So I hope it's clear. Now we'll move to its code. So here is my code for it. So first I have took the inputs, then I have taken in the array ARR. I have the value stored for each inputs. Now the first thing we will do is we will find the minimum index. So this way min e sorry min I will store the minimum index value. Then we have to make arrangement for DFS. So this is the adjacency node. Then this is the listed array. Then in this vector v, we will store uh, how we are removing the uh, nodes from the graph. So we will eventually print this v as an answer. Suppose this was our graph. Then we will store the order in which we are removing the nodes. So first, let us see our DFS function. So this is typically what we do in DFS calls. Uh, I will I will call the DFS for the minimum index value. Here you can see I have made a DFS call for the minimum index, and since I have done this for one base indexing, so I have called it for min I plus 1. So here is a DFS function. I will first mark the node that I have visited. Suppose uh, say, take an example. Suppose this is our graph, and this is the minimum index. So I will start the DFS call from the minimum index, that is 1. I have assumed that this is the minimum index. Then I will mark it listed, and for all the adjacent node, I will call the DFS again. So first, what will happen? Wait, there will be call for node 2 and node 7. Then there will be call for node 3. Then there will be a call for node 4. Then there will be call for node 5, and there will be call for node 6. Now there will be no further calls, so we will come out of this because here only call for the adjacent nodes are made. Now after that, we must have reached the leaf nodes. So from here, back propagation will start, and then we will start putting the values in our vector v that we created here. So first 5 would come in this, then uh, from 4 uh, there will be, then 4 will be removed, then it will 4 will be removed, put inside this vector v, then 6 will be removed, uh, then it will be put inside vector v, and since all the back propagation are done till node 3, so after that there will be back propagation for node 3. Node 3 will be removed, and this will be put inside our vector, and similarly all we will visit all the nodes in the back propagation and put them in our vector v. So here up to here it's done. Now we need to, in the question we need to print the size also. What is the total number of nodes that we remove? So it will be equal to v dot size minus 1. This represent only one element, that is the minimum element. This is not counted, else all the elements are present. Now I have built the uh, first m minus 1 elements. So total there was m, but now only we will print only m minus 1, leaving the node which was the minimum, which has the minimum index. So in the back propagation step, you can also see that first the leaf call for leaf nodes are made, and the last call for back propagation is made for the one with which we started. Because back propagation we have discussed till 3, then after that the function will return to 2, then 7 will also return, and then 1 will be the back propagation process. So this is our answer. I hope it's clear.
So this is problem E here. Break the string. So we're giving a string S consisting of lowercase English letters, okay? Then you have to count number of ways to break the string S into 3 strings, or 3 substrings rather, that is P, Q and R, such that concatenating P, Q, R in order produces S. That is, we just break the string S into 3 pieces. The substrings can be empty also, mind you. And this is the second condition we have. Concatenating P and R in order produces Q, that is P plus R equals to Q. So this is the main condition here. This is around which the whole problem is based. Let's just quickly check out the constraints. We have the length of S is from 1 to 3, 5. Okay, so let's try out the test cases first. We have double A, double B here. We have A, and bb here. So can we choose such a pnr? Can we break the string into pnr such that the whole string is this was that p plus r equals to q, the middle one. So from trial and error we can just see that we can try to break it like a b and a, right? A b and b, this is p, this is q, and this is r. So if we concatenate p plus q, p plus r, then we obtain q, right? So this is one possible combination, and there are no other possible combinations that we can make from this string at least. So we can just draw out one conclusion. If we want to split a string, let's say we want to split into p, q, and r, right? Such that p plus r equals to q, p plus r equals to q. Then we must have one condition that since p plus r is q, the first characters of p must match with the first characters of q, right? And on the leftover string q, the characters of r must match. What I'm trying to say is that if we have a string, I'll split it into p, q, r, we should be able to split q into strings a and b, right? Such that a equals to p and b equals to r, right? Since obviously since q is equals to p plus r, then we will be able to split it into strings a and b such that a equals to p and b equals to r, right? Then basically our string will be of this form. We have p, p, and r, r. We should try to find such p and r such that the whole string can be split into p, p, and r, r. This will be q, this will be p, and this will be r, right? This is our main focus of the problem. So let's try it with another example. We have double a, double a, double a, 6 a's we have. So how can we split it? If we take the first two characters as p, then we'll have to take another two characters because we have to find pp. So this is also p, right? And then we have to take r from the back. So we'll just make this as rr. This is possible to split as pprr. This is one such method. Can you find another such method? So okay, what if we just split the string like 3 times, like in 3? So we have the first string p, and which is another string p, that is triple a again, that is also p, and then we choose both the next two r's as empty strings because it's possible, right? So this is also another possible split, right? We choose two p's and two r's. Similarly, can we just do this from the back also? uh, it's very similar to what we did. We have 6 times a. So if we choose these two as r and these two as r, then this will become p and this will become p. So this whole string will become q. So such a split is also possible. This is the third possible split. And the fourth one is also the reverse of this string. Like we choose r as three strings, 3a's. So this is r. And then we take another r. We have 3a's. That is also r. And then both the p's will be empty substrings. So this whole string will be q. This will be p. And this will be r. So this is the fourth possible split. There are no possible splits in this, right? Okay. So we basically have to check. This problem is about checking for common substrings. Like since we have to split it into 4, okay. Suppose I'm at this index, I want to split at this index, then I must have the next few characters. Like if there are x characters before this, Then the next x characters also match with the first x characters of the string, right? And then the remaining characters, let's say this is y characters, or let's say the remaining string length is y, right? Then y must be equals to an even number. If you want to split this into two equal strings, substrings, right? And y must be even, and the substring x plus 1 to y by 2. I'm talking about this plus x. Okay. This is x plus 1 and this is y by 2 plus x, right? This substring must be equals to uh, y by 2 plus x plus 1 to y, basically y plus x. Sorry for the bad handwriting. Y plus x, right? This is the basic condition here. So we just keep matching strings, like this string must be matched with this string, and then we take the remainder of the string and try to match this string with this string. So this is basically a string matching problem. We do not have to apply much of logic here. The logic is pretty much simple. We have to split the whole string into p's and r's, and we just have to calculate if it's possible to split it into two p's and two r's. And for each position, we'll just calculate that number. So how do we match the string? Obviously, if we put a naive algorithm, right? If we go to some index I, then try to match like I minus 1 characters with the next I minus 1 characters, right? And then we try to match this again. Then this will be of n squared time complexity. So what are the constants here? Uh, okay, so n is from 1 to 3, 5. So obviously we cannot apply n squared time complexity. This is not possible. So we'll have to apply some kind of a hashing function to the string for matching the string quickly in short time. So what we can do is, in my case, I just use Z algorithm. If you're unfamiliar with what Z algorithm is, please do read it in the CP algorithms website. I'll just put the link for the algorithm there. You can read it from there. So I've just applied Z algorithm to check for the length of string that is matching. For example, like for now, if you don't know Z algorithm, just consider that Z algorithm gives you an array of n elements, right? And each element of the array will give you the number of matches number of matches starting with I, and by matches I mean character matches, right? With I to the string, the whole string that is of length n. uh, for example, for those who don't know Z algorithm, I'll just give a short example. I won't run the algorithm here. I'll just give a short example to get an idea what it is. If you know what it is, just skip to the later part of this video. So let's say the string is a a b, and then again let's say we have a a a b, right? So this is the whole string, right? So the first element of this string, if we take the first element of this string, we start with the first element, then this whole string will be matching with the whole string, right? So here the z function will give me n, the first element of the z array, that is n, because the whole length is being matched. If we start with here, right? So the first character matches with the first character of the string, the second also matches the second, but the third does not match with the third, right? So a substring of length 2 is matched here, right? So this will give me 2. Similarly, if we start with the third element, the first element will match with the first element of the string, the second element will not be match with the second element. So it will just give me one, right? One character match is what we found. Then we go to the fourth element, then the first character does not match with the first character itself, so we break and we print 0. So this will give me 0. Similarly, if we start again with A, so the first three characters match with the first three characters, and the fourth character also matches with the fourth character. So this will give me 4, right? And again, if I start with the next A, the first character matches with the first character, the second character matches with the second character, but the third character does not match with the third character. So that will just give me 2. And if I start with here, it will give me 1, and then again 0. So this will be my Z array. And this array will be computed, I'm sorry, array. So this array can be computed in O of n time complexity. That's the beauty of Z algorithm. It is a very nice algorithm. You can just read about it. So once I compute this array, I can just check, like earlier you were checking now. Okay. Earlier you were just checking that if you can find two p's here. Like if you want to break a substring here, can you find another string of length p here that matches with the first p characters, first x characters, right? So we can just do that by Z algorithm. If this element of the Z function will be equals to or greater than equals to x, then we can just say that this the next string matches with the first x character of the string at least, right? And then we can try to split the rest of the string. So on the second part of string, how do we find 2r's? Like we have to match this with the ending part of the array, not with the starting part. But this will only give me number of matches with the starting part of the array. So how do we solve this problem? For this, you can just reverse the string, and take Z function. Because finding 2r's from the back is the same as finding two p's from the front, right? 2r's from back is equivalent to two p's from the front, right? From front, right? And they should make the whole string, right? So that's what we'll be doing. We'll be just taking two Z functions, one from front and one from the back, and we'll try to find such a set of strings that can match our conditions. We'll try to find two p's and two r's basically. So let's get to the solution here. Okay, why did I take a screenshot? I don't know. So let's get to the solution here. So suppose ZF is equals to the Z front array, or let's just say it is the Z array from front, right? And ZB will be Z array from back, right? Okay. So Z will be B will be equals to Z array from the back. So in ZF we want to find two p's. So if the ith element is the Z front function, you know, right, I'll just write it as Z of I is greater than equals to I. Here I'm talking about zero based indexing, right? So if we have 0, 1, 2, and I is the third element, then there are three elements behind this, right? So if ZFI is greater than equals to I, which means we have found two P matchings, right? And then we'll just move I positions further until 3, 4, 5 is matched, and then we move to sixth position, and then we will split the string further. Let me just draw it with more clarity. Okay, suppose we found I such that ZFI is greater than equals to I, right? So this is 0, 1, 2, 3. Then we'll match till 4, 5, 6, and from 7 onwards we will look for another array, like we'll look for 2 R's. So for that we'll look in Z back, and similarly we'll check if there exists an I such that we'll basically just split it into 2. So this will be, if this whole string length is y, then this will be y by 2, right? So for Z back it will start from here, right? So if ZB ka I by 2, or rather y by 2, is greater than equals to y by 2, then such an R exists, right? So that's basically what we'll be doing. This was just a hashing problem. I'll just show you the solution, you will understand very easily. So the solution itself is not that difficult. So this is the Z function here. This calculates the Z vector, as you can see, of a string S and returns it. So first we take input, then we find the Z front of Z function of S, and we reverse the vector, reverse the array S, and then we find the Z back, the Z function of the reverse string, and then we reverse the string again to make it back to normal, and then initiate a count, like the number of possible ways we can split the array. So we'll iterate from 1 to from 0 to n, right? And similarly, like I told you, if z of I is greater than equals to I, okay, then the remaining length here, that will be n minus 2 times I, right? Just for example, with indexing, let's have an array of length 7, 3, 4, 5, 6. So the arrays of length 7, that is n here, and suppose z of 3 is greater than equals to 3, right? So the remaining length of the array will be 7 minus 2 times 3, right? That will be equals to 6. So yeah, that will equals to 1. I'm so sorry. This is equals to 1. So one element is remaining, and now we have to check for z back the remaining size, right? So that's what we have done. If remaining length is even, right? If remaining length is odd, we cannot do anything. Like for in this case, if remaining length is 1, then we cannot split this into two strings, right? It is impossible to split into two equal strings. So then it will not be possible. But if remaining length is even, then what we can do is we take half, this is remaining length by 2. Like I told you, this will be y by 2, the last part, right? And we'll find another y by 2. So, yeah, we'll have to find another y by 2 of z back. So the half is remaining length by 2, and then if z back of half is greater than equals to half, like I told you, just very similar to the front problem we are checking. If z of I is greater than equals to I, it's the same thing from the back. So if zb of half is greater than equals to half, then we just add 1 to count, because that's a valid string, and we just iterate this from 0 to n minus 1 with a 0 based indexing. So that's it. We just print the count. uh, Obviously it's accepted, you can see here. It was pretty easy problem. So that was about hashing function or z algorithm, you can see, and that's it.